So carbon sequestration is what I'll talk about today. I'm the reservoir program manager. So I think about reservoir rocks, rocks that you can store any kind of fluid in, whether, you would think about that in other states about oil and gas, getting oil and gas out of that.
Right.
In Washington, we don't have commercial oil and gas production. So carbon sequestration, you can pump a fluid, you can pump carbon dioxide into the rock and have it stored there. So what I wanted to talk about today was the reservoir, that's the rock that the CO2 would be stored in.
Okay.
The seal, which is the cap rock, it's the rock that would block that CO2 from coming out.
Okay.
And at the end of the day, I hope we can see there's a little bit of structure that we'll also be able to see too. So that's trap. That's if you have a reservoir and there's buoyant fluid in there and wants to get up, you need a trap. You need a rock in a certain configuration, a certain shape that it's going to hold that that fluid back.
So you're talking to somebody who's been in geology a long time, but I know nothing about this topic. So I'm going to ask some really dumb questions.
That's great.
Okay, Will?
Mm-hmm.
What are we trying to get rid of? Why are we why are we storing some of this material? Where's it coming from?
So when we burn fossil fuels, we turn those fossil fuels, they're hydrocarbon chains they've got carbon, hydrogen, oxygen. We burn those. And the carbon and the oxygen form carbon dioxide. They go up into the atmosphere. When the sun's rays hit the earth, some of that heat wants to bounce back, and a lot of it gets trapped when it's trying to bounce back and go back out into space. So we're holding a lot of that heat in from the sun. That's called a greenhouse gas, CO2. There are lots of different kinds of greenhouse gases, but this is one that we can control how much we're putting up there, either by reducing how much we emit, and then while we're waiting to come up with new technologies to reduce how much we emit, we can also capture the CO2 that's already there, either by capturing it from the flue gases from factories or refineries, power plants, the gases coming out of the smokestacks. You can capture that, compress it, and pipe it, and then inject it into the ground, into a reservoir rock. Or there's something called direct air capture, where you can capture the CO2 directly from the atmosphere with slightly different technology.
Okay, wow. So that's happening now? People are capturing?
So since the 1970s, CO2 has been captured and then injected into the ground in a process called EOR to get more oil out of the ground. That's done in West Texas. They've been doing that at the Sack Rock field since the early 70s.
Yeah.
But here in Washington and a lot of the other places where you don't have oil and gas production, you can just pump it into the ground and not produce more fossil fuels from that. And they've been doing it offshore in Norway since the early 90s, pumping into the Sleipner field in the North Sea. So this technology has been around for a while. So the reason I wanted to stop at the Ellensburg outcrop first was just to give people a sense of I want to talk about what was used to be called a conventional reservoir is.
Oh.
So you think about reservoirs as sandstones or limestones, sedimentary rocks. And the reason why I wanted to start with that basis is Washington is a unique case where we've got the potential to store CO2 in basalt. And basalt is not usually thought of as a great reservoir rock, but I'll show you by the end of this, there's some great reservoir potential in the basalt. And the other reason that the basalt is exciting, other than that it covers half of the state, is that once you store the CO2 in the basalt, it reacts with the basalt to form carbonate minerals. So it forms solid minerals, and then you don't have to worry about these plumes of gas or fluid. I'll talk about the kind of fluid it is, the phase it is in. But you don't have to worry about these plumes migrating and watching where they'll go. Because if they solidify and form carbonate minerals, then they'll just be stuck in place.
Okay.
Yeah. The reason why this is a terrible reservoir is that a couple of reasons. It's got it's poorly sorted, so that you end up having big grains of sand, and then you have lots of little grains of sand in between them. But then you also have a lot of clay material, and you have a lot of because of the mineralogy of these coming straight from, we're pretty close to you can't see it on the skyline, but we're pretty close to the Cascades. A good reservoir rock will have good porosity. Porosity is the space in between the grains of sand, or whatever the sediment is. And then you also need permeability. So permeability is connectivity between those those pore spaces, between those voids in the rock. So if you're thinking about a reservoir, don't think about it like you might see in certain movies as like a river underground, or a big, there's a giant cavern with a lake. If you're thinking about water resources or oil and gas resources, there's almost always not a giant lake of oil underground. What it is it's oil or water or gas filling in those void spaces, those pore spaces in between the sand grains. So what you want to do is you want to maintain the porosity and the permeability. So you want a hard grain like quartz that when it's buried very deep underground, and everything I'll talk about today when I'm talking about the carbon sequestration, it's not going to be happening at the surface. It's going to be happening about 2,000 or 3,000 feet below the surface. Okay. But I'm using these outcrops on the surface just as an analog, because we can't look at what's way down there. So you want to have hard grains that are going to maintain that porosity, and you're also going to want to not have too much of these clay minerals that are going to clog up the permeability and not allow it to flow.
So if we had a big wad of this stuff in the subsurface between basalt flows, and you want to store, I still need the right phrase. What you're trying to store fluids that have the gases in them, or you're trying to pump the gases in?
So the gas has to be very pure. So it has to be about like over 99% CO2.
Okay.
So when you're capturing it from a power plant, or if you're capturing it from direct air capture, just from the ambient atmosphere, you then have to separate whatever other gases are in that.
Okay.
To have it a very pure CO2. And then you have compressors. They're basically turbines, or you could have giant piston compressors that squeeze it into something called a supercritical state. So when you're a kid, they teach you that there's solids, liquids, and gas, but there are other phases too, and one of them is supercritical fluid. And what that is it doesn't have to be that cold, it just has to be at a pretty high pressure. And then it has some of the properties of a gas and some of the properties of a liquid.
Wow, you're blowing my mind right now.
Yeah. So
you get this supercritical fluid?
Yep. So that's why I keep calling it a fluid.
Okay.
So gas and liquid, they're both fluids. They can flow. So I'll keep calling it a fluid instead of a gas, because it's not actually in a gaseous state when you're injecting it. In all the projects that have been applied for or that are active in the U.S. In Iceland, they have basalt sequestration, and they inject the CO2 as dissolved CO2 in water. You could have, and mineralogically it might not be great, but just in terms of the grain sizes and the sorting, like this might be better. But then you have, let's say, above us, or if you started below us and you were in some of that nice sand, if you had a fluid that were buoyant because of all that pressure that's squeezing it, it wants to come up to the surface. Everything wants to flow up when you're at these great depths. So you think of it as the opposite. When I talk about the structures later, I'll do this with my hand a lot. That's like it's called an anticline. If you were at the surface, where in the Yakima Fold Belt, it's great. Some of these anticlines are at the surface. When it rains, the rain falls down. But if you're buried very deep underground, the pore pressure of all those grains squeezing, just because of the overburden, the weight, it's squeezing the fluid that's in between them. So that fluid wants to go up. It wants to go to in the direction of least resistance. So it's going to want to go up to the top of that structure.
This is like the worst possible state for finding.
No,
it's not.
No, it's not actually. So that's what's been interesting about the carbon sequestration studies over the last few years, is that a lot of states that don't have oil and gas, the states that have oil and gas, they've studied their reservoirs really, really well, so they're at the head of this. But a lot of states that have very minor oil and gas productions, like Alabama, Nebraska, they've gotten their programs started to try and get carbon sequestration going, because they realize they have the reservoir rock. It just, it hasn't been producing oil and gas. And in Washington State, we've had oil discoveries over on the west side. We've had oil discoveries here on the east side. In the 80s, Shell was out here drilling these anticlines also. They were targeting sub-basalt. So in the Eocene rocks that are below the basalt, there's more sedimentary rock down there. It's just all these Miocene flood basalts covered all that up. Puget Sound Energy, the biggest private utility in the state. They've got a natural gas, underground natural gas storage site, the biggest one in the Northwest in that rock. So that means that they've proven the reservoir. So I was saying, like, this is the container. In that case, it's cheaper to store the natural gas in the rock than it is to store it in giant containers on the surface. So in the winter, people are using the natural gas to heat their homes. And in the summer, so they're producing it out of those reservoirs. And in the summer, they inject that natural gas into the sandstone. So they've got injection wells and production wells, just like you'd have with carbon sequestration. So it's not just carbon sequestration that's had this injection of gas and production of gas, but also the natural gas that we're using to heat our homes. So that's in that Eocene sandstone over on the west side. So it makes a great reservoir. They've also got seal rocks too.
All right, Will, so far, I think I've got the concept that we're taking the carbon dioxide, we're mixing it with a fluid of some sort.
We're not mixing it. It is the fluid. We're just squeezing it real hard into a supercritical state, and then we're injecting it.
And we're ready to pump it or inject it into some sort of reservoir. And in the case of Eastern Washington, surprisingly to me, we're thinking about this as a reservoir. Basalt lava, which we've got plenty of.
For supercritical fluid, you want it to be more than 800 meters below the surface, just because then the weight of the rock on top of it keeps it under pressure, so keeps it at a supercritical state so that it doesn't turn into a gas. You know, the pressure isn't released and then it turns into a gas. So you want it to be deep. So these rocks here are something called, they're near the top of the Grand Ronde. Grand Ronde is the most effusive of the Columbia River basalt units. So, you know, if you think about it stretching, 17 to 6 million years or so, this is only, I think it's less than 1 million years.
400,000 years.
Yeah. So during that period, and it's like 90% of, I don't have the graph, I have it on my book in the car.
Yeah, these are the big boys. These are Grand Ronde flows, and you're contemplating, or this has already happened, pumping some of these fluids into this Grand Ronde.
So it's already happened at a pilot test. So the first place ever where CO2 was injected into basalt was at Wallula Gap.
Okay.
There was a well drilled in 2009, PNNL, the Pacific Northwest National Laboratory. They were involved in, they were the PIs on that, the principal investigators on that. And they drilled into the basalt. So Wallula is over by, it's sort of a little bit to the south and a little bit southeast of the Tri-Cities. Yeah. So near the Oregon border. They drilled down and they drilled into the Grand Ronde. They found some nice reservoir units in there, and they drilled 1,000 metric tons of CO2. So 1,000 metric tons is just it's a test case. So if you want this to be done on a commercial level, you'd need a well that would be able to inject 1 million metric tons per year. So a lot more than that. But what they did show with that 1,000 metric tons is that they monitored it, the well, and they took tests in the years after the injection.
Okay.
And they found that and they took cores also before and after, and they found that the CO2 had mineralized into, within 2 years of injection, I think about half of the CO2 had mineralized. So it was an even faster rate of mineralization than they expected.
It's turning into a solid?
Yeah, it's turning into a solid. So then...
Why? How's that possible?
So so if you have a lot of iron and magnesium that are free, they're able to be released from their crystal structures.
Wow.
In the basalt. If you've got a lot of those available and then you pump down CO2, then you form a carbonate mineral. So most people are familiar with carbonate minerals from limestone or even marble that you might see as beautiful sculpture or a building stone is just a metamorphosed version of limestone. Right. And limestone is CaCO3, so it's the carbonate, the CO3, mixed with calcium. But you could do the same thing with other minerals. So dolomite is magnesium and calcium mixed together with that carbonate. So if you get the CO2 from that you're pumping down there, and you mix that with iron and magnesium, and there might be a little bit of calcium in there too. You can get a mineral called anchorite, and anchorite it's iron, magnesium, carbonate. It's a solid.
Wow.
So then you don't have to worry about that fluid, moving around too much.
Well, that was my initial thought, is that, this basalt is so heavily fractured.
Yes.
I'm just imagining pumping a fluid into this stuff, it's going to just leak out or get out of the host immediately. But you're saying that this transition to a solid is a real thing.
Yeah, so the transition to a solid is fast, but then also, so you want to get it into, we talked at the beginning with the sedimentary rock about porosity and permeability.
Yeah.
And if we could get up to a face of this rock that doesn't have too much tumbleweed, you can see beautiful porosity in this. And the porosity are all these vesicles. So if you get right up to this, it's just chock full of, it looks like moon rock, what people imagine moon rock to look like. It's just filled with all these holes. And what these holes are from are, as the lava is flowing, there are gases, there are volatiles in the lava that are coming out of solution. So they bubble up to the top. But then if the lava cools with some of those bubbles before they reach the surface and pop and go into the atmosphere,
right,
then these bubbles just get frozen in time, and that's what you're seeing. They call them vesicles, and all these vesicles are porosity. So then what's the permeability? So the permeability is all the fractures. The vesicles are as I mentioned, they're coming to the top of the lava flows. So the flow tops are those vesicular units,
right,
but the flow tops are also the tops, the part of the lava flow that is, it's cooling and it's cracking. And so all the fractures that cut this up, you call this breccia. It's just, you see these chunks of rock. Sometimes a part will cool faster than another part. Or if it's flowing like this, there might be sort of like a caterpillar tracks factor going on, where stuff from the top is falling off the nose of this lobe that's moving as the lava flow moves. And so it's all brecciated, and all the fractures between that's your permeability. That's connecting all these pores together. So if you drill a well, it might be, this diameter.
Okay.
You drill that through here.
Right.
Then you can access all these pores through the fractures that are cutting through it. But then the question is, how do we seal it? How do we make sure it doesn't flow out the top?
Exactly.
And that's what the top unit is here, is an example of the colonnade. And the colonnade has been shown in water wells to act as a great seal between drinking water aquifers. And this is all happening, all the carbon sequestration is happening a lot deeper than any kind of underground source of drinking water. But what has been shown is that that crystalline rock, it doesn't have the vesicles in it. That serves as a good seal. But everybody who drives past a basalt outcrop of the colonnade, they see that there are these vertical joints in them, or fractures in them.
Yeah.
And so they think, well, why wouldn't those joints just serve as a conduit for all this fluid to flow out? And what's interesting is that I think you've talked about the Yakima fold belt in here. There are tectonic forces in action here, and those tectonic forces end up making something called the horizontal axis of stress. That's the highest axis of stress. Usually when you're really, really deep underground, the highest axis of stress is your vertical one. There's so much weight pushing down that's what's holding a lot of fractures closed. But in this region at depth, it's the horizontal axes are the highest stress axes, and these, so deep down underground, these fractures are being squeezed together by tectonic forces, and that's holding these fractures closed. There's also the fact that at depth you can have clays filling these that you don't have at the surface. That, as we mentioned with the sedimentary rock, that clays also form a really good seal to block up your permeability. So you do want your permeability blocked in the seal rock. You don't want anything flowing through it.
That's it.
So,
the difference is at depth. This just seems so loosey-goosey and so fractured and so riddled with holes that you wouldn't keep anything there. But if you're at depth,
it's all squeezed together, and all those fractures
together.
are closed.
It finally kind of works for me. Yes.
And then, in addition to that, one other thing I want to mention, maybe we'll walk down here, is that you also, the EPA has rules, so just like an oil and gas reservoir, which has a structure, a trap that's holding it back, the EPA says you have to prove that there's a structure in your area. So you can't just drill these wells anywhere, even though even though the CO2 is going to mineralize really quickly. You've got to find a place where during the period when it's not fully mineralized, it's not going to flow out, not just because there's a seal, but also because there's a structure. Because let's say you have an incline like this, a beautiful seal on top and a reservoir below. If you drill into this, that CO2 is going to flow up here. What you need is that seal rock to then be in a structural position that it's going to flow up here, and then it's just going to get trapped at the top of that structure.
So you've already earmarked the places that you could drill in the next decade to pump a bunch of stuff down?
So there's something called play mapping, where you look at the depths, you look at, if people get around to drilling some of these, they're called stratigraphic test wells or pilot wells, they can get a better sense of like where the best reservoir is. If you drill enough of these test wells, you can then map that out and see how extensive those units are, and then you could start building from plays down to something called prospects. When you're exploring for a resource, you call it prospecting, but we're prospecting for pulling the CO2 out of the atmosphere here. So as we collect more data, then we can get a better sense of where those locations are. We've got a couple of locations that we're looking at right now. We've got money then to shoot, acquire seismic. It's not, you don't use dynamite for this. Okay. It's in the past it would say shoot seismic. So these are vibra-sized trucks, where we're acquiring seismic over a series of these anticlines to the south of here near the Oregon border, and then the Carbon Containment Lab is then collecting other geophysical data to try and get some of that information about the subsurface. Because it's great, you can get an analog by visiting the outcrop, but before you want to drill in a specific location, you're going to have to get some of that seismic data and some of those other geophysical data to try and understand what those rocks look like in the subsurface. You can't drill everywhere, that's too expensive.
Thank you, Will.
You're welcome.
A great, interesting topic. I knew nothing about it. I know a little bit more now.
Yeah, I'm glad. Thank you for helping to spread the word on it through these videos. It's great. Or everything that the WGS does. So,
yes.
Thanks a lot.
Thank you.
Thanks.